in my introductory lectures, I talked about causal inference. I didn't go into a lot of details. Actually, when I'm teaching, I usually would spend quite a bit of time on some of the more basic connections between econometrics and machine learning. But specifically in macro and finance, you very commonly have these longitudinal data sets. And so for this particular conference, I wanted to jump right into that because that's a part that's more likely to be familiar to you. I should also want to say at the very beginning, to be fair, that if someone who's already familiar with the econometrics literature might feel a little bit annoyed in that they might say, well, we already knew a lot of this stuff and we've been doing kind of factor models all along. So what's new about machine learning? And I would sort of agree, actually, that there's more close connections to the econometrics that's been done in the past by people like Serena Ng and Dushan Bai and others to what machine learning would do. And that may be partly because a lot of the problems that we've looked at in macro and finance actually were prediction problems to start with. And so it's not surprising that the way people approach prediction problems across fields is sort of closer together than where I have been talking in the last lecture about the distinction between causal inference and prediction. So just to summarize that, I would say the contributions of machine learning to the smaller parts of economics that have focused on pure prediction problems may be more incremental, maybe more computational, and less big picture conceptual than in the micro literature where we're taught really to focus on these simple, like pre-specified God of economics given models. Okay, so let me start with a motivating example for thinking about longitudinal data. And this is coming from, this still actually is a causal inference problem, by the way, but you'll see in a minute why I'm calling it more of a prediction problem. We are trying to understand what is the causal effect of a California anti-smoking legislation on smoking rates in California. And so for this, we can think about what data do we have to answer this question. So we might observe smoking rates in California in 1989. We also have data in the absence of smoking legislation in California prior to 1989. And we have data for other states both before 1989 and in 1989. And we have other variables, but I'm just going to focus on the outcome variable here. So the main focus can be a setting where you don't even have any covariates. You just have the outcomes. Okay. And so what is the problem? Well, if I want to understand what was the effect of the legislation, I see California with the legislation in 1989. I need to impute or predict the counterfactual smoking rate of California in 1989 had the legislation not been enacted. Okay, so that's the prediction problem that we're solving. So we can visualize this as a matrix. So here I've got my matrix of outcomes, and so the rows are the units and the columns are the time periods. And then we also potentially have a matrix of treatments. So here I've just showed it, you could be 0 and 0, 1, but usually with legislation, actually, you're going to have kind of a block design where, a state adopts the legislation. And so a particular row might have all ones after a certain time period. But in principle, you could have treatments turning on and off. Okay. So this is the setup of how we're going to think about the data. And if I think about it from a causal inference perspective, I can think about it in terms of potential outcomes. So for those units and time periods that were not treated, I have check marks. I observed their control outcome, but in the periods and times where those units were treated, I have a question mark because I don't know what their potential outcome was. And similarly, Y of 1, those are the outcomes you would have under the legislation. And so for each of these units and time periods, I either see their treated outcome or their control outcome, but I never see both at the same time. Each of these cells either has a check or a question mark. And so that's the missing data problem of causal inference. So what does an average effect look like? Well, in principle, if these treatments were randomly assigned, I could just estimate the treatment effect by comparing the treated and control. But in principle, what I would like to have is, for each unit and time period, there is a counterfactual treatment effect, the difference YIT of 1 minus YIT of 0. For each unit, there is a treatment effect. So ideally, the overall average treatment effect would be this the average of the treatment effects for every individual. But of course, we can't just calculate that, because for each individual, one of these two things is missing. And so it becomes, again, a prediction problem. So one approach to this is called matrix factorization. That's what it's called in the machine learning literature. In economics, we would have called it just factor models, and they've been used in other disciplines too. So first of all, let's just build some intuition for how this works and why it's a likely to be a successful approach. So we can take this N by T outcome matrix, and we're going to think about expressing it as the product of two matrices. One of them is N by K, where K is going to be a number of factors. And the second is K by T. And if you remember your linear algebra, multiply N by K times K by T, you get back an N by T. And so what this really says is that, each cell in the big outcome matrix is going to be the product of a row of the first matrix and a column of the second matrix. And the way I think about that is that there are these factors that that are determining outcomes. So in the smoking case, we might think of it as there's different demographics. And so, maybe there's different ethnicities or different kind of socioeconomic factors. We have a certain number of rich people, a certain number of poor people, a certain age distribution. And so there might be differing smoking rates in every cell. Then the time factors would basically be the smoking rates for that cell. So suppose California was, half rich and half poor, then we would take the dot product of 0.5 times the per year smoking rate for rich people and poor people. And we would put that together and say, oh, that's the smoking rate for California. Now, so there's going to be one set of smoking rates for rich and poor people in 1980. There's going to be a different set of smoking rates for rich and poor people in 1985. But as long as the income distribution of California didn't change, those loadings could just be applied. The 0.5 for California could be applied to the different average smoking rates for rich and poor people in the different years, and that would tell me what the smoking rate in California was. Okay, so that's kind of the interpretation of these. Now, the way that economists traditionally thought about that is they said, well, like the God of economics said that there are 6 factors. And, then we tried to figure out either we would just pre-specify 6, or we might have some data-driven way to decide whether there were 6 factors or 7 factors or 8 factors. But the way the theorems looked mostly, or like the main, there's always exceptions, but like some of the main theorems would have the form, suppose there are 7 factors and the data set gets bigger, can I recover those factors, and how would I recover those factors? And so then there were tools that would help you do that. The machine learning approach to this has just maybe a slightly different aesthetic to it. The machine learning approach would say, probably there are lots and lots of factors, but I want to find the number of factors which comes up with the best approximation for my original matrix. So it would be more of like a mean squared error, a bias variance trade-off thing. If I have too many factors, I might overfit my data. If I have too few factors, I might I might be giving the same predictions for everybody. So I'm trying to find the right balance of the number of factors to have a good approximation for this for my original matrix. So, and then just a little reminder of theory from, if you forgot this from your linear algebra class, don't worry, many people did. But there are basically theorems in linear algebra that tell you that you can always represent an M by T matrix in this way for some K, and that's going to relate to the rank of a matrix. And if you remember what a singular value decomposition is, that's a way to represent the matrix using this kind of a factor representation. But when we think about it from an approximation perspective, you can also well approximate a matrix with a lower rank matrix. And so in principle, there's going to be, in general, it's a general fact that there will be a lower rank approximation for a bigger matrix, as long as there's some structure in that matrix. So thinking of it from a more of an approximation perspective, you might use something like cross-validation to figure out the number, the number of factors. But it turns out that's not actually going to be the best approach computationally. And there are other approaches to try to figure out the best kind of best factor approximation, other than just testing out different numbers of factors. And machine learning is going to have those. So I'm not going to go into a lot of those details now, but just to say that it's easy to think of the idea is just testing 2 factors, 3 factors, 4 factors, 5 factors, 6 factors, and coming up with the best. But that's not actually what the best machine learning methods do. They do some things that are a little different. And I use something like called nuclear norm minimization in some of my papers, for example. So we can think about writing this down, this outcome model. The outcome model models each the outcome in unit I and time period t. It can also depend on observables. So the x's and the z's would be observables. We might model fixed effects, like fixed effects for the unit and fixed effects for the time. They don't need to be modeled, but in some economic settings, it's important for identification of a causal effect, or there's some reason why you really want to include those. When we go to figure out to kind of do this prediction, as I mentioned, there's more than one way to solve the minimization problem of finding this low rank approximation. And nuclear norm, in some of my papers, we argue has some nice advantages, but let me not give you those details here. Let me instead kind of show you a little bit more the way that this actually could work in practice. So in this illustration, we're going to start with a data set of stock returns over 10 years. And so if we want to sort of test our methods, what we're going to do is we actually observe all the stock returns, but then we're going to imagine for this simulation exercise that there was some policy change or treatment that affected some of the stocks and some of the time periods. So we're going to sort of imagine that maybe, there was a information disclosure regulation that applied only to big stocks over a certain time period, or they applied only in a certain industry. So that's the kind of policy problem we would have in mind. And so the way that we're going to be able to tell if our method is doing well is that we're going to imagine that a certain block of the matrix was treated. Then we're going to see how well we predict the counterfactuals. Of course, they weren't treated. This is just a fake exercise. So we'll say our method does well if we accurately predict those missing values, which just gets back to the fact that this is really a prediction problem we're interested in. So in order to kind of make this comparable, we set up this simulation study where we keep kind of the total number of missing values fixed at 4,900, and we actually change the shape of the block that's missing. So in some cases, the block that we're trying to predict, again, the fake treated block, is going to be 10 by 490. So it doesn't have very many units, but it has a long time period that's missing. While we also take the case where there's only a short time period missing, but there's lots of units missing. And then we also take the case in between. And the reason we're trying these different shapes is because different methods for doing this prediction might be better at picking up cross-sectional variation. Other methods might be good at picking up time series variation. And then, some might do better if there's something in between that's missing. And so we run the simulation exercises where for each shape of the matrix, we sample different stocks or different years to be missing. And then we see how well we do in prediction. And so what we have here is what the kind of mean squared error looks like, the root mean squared error that's normalized. And we're trying a couple of different approaches here. So the matrix factorization is the red, and it has the lowest mean squared error across there. And when you're doing methods comparisons, that's of course what the author of a method always shows you. They show you a nice picture where their method does best across a whole range of things. So not surprisingly, my method is red and it's got the lowest mean squared error. So surprise, surprise. And generally, you kind of keep working on your method until until you get there. The other two methods are what we call horizontal and vertical regression. So just going back to the, let me find a picture of, go back to a picture of the matrix to start with. If we think about running a regression with just a big outcome matrix, if you have something that you're trying to predict, one thing I could do is I could take the last time period and regress it on the previous time periods. So that would be like saying, I think the best predictor of the last time period is, yesterday or the day before. And that's one kind of method people use in practice. They, you say the left-hand side is this column here, say the last column, and you regress it on the past. And that would work well, like if there's a lot of serial correlation, if the best predictor for any unit is just what it was yesterday. Okay, so that's one kind of approach. Now, if you think about when you can use that approach, you can use that approach if you're going to run a regression, you need there to be more observations than there are covariates. So if you have kind of a tall, skinny matrix, you don't have a lot of history, but you have a lot of units, then it's really easy to run a regression of today on yesterday, because there's like one covariate and lots of observations. On the other hand, if instead I had lots of time periods and not very many units, then if I regress today on yesterday, or today on the past, then I might have lots of the past and not enough units to actually run the regression. So regressing today on yesterday doesn't work very well if you have a wide matrix. So on the other hand, you can go the other way, something called synthetic controls, which is used a lot in causal inference. You could regress one of the rows on the other rows. So suppose, the one that was treated like this unit in is California, the synthetic controls approach to figuring out the effect of the smoking regulation would be basically to regress California's outcomes in each year on the other states. So then you would be saying each state is a convex combination of the other states. So California is a convex combination of Arizona and Nevada and something else. And that would work if you have lots of time periods and not a lot of states, because then you could regress, then you have lots of time periods to be the units in your regression, and you could regress them on the other states. So in this example, we're comparing this regressing the one time period on the other time periods, or regressing one stock on the other stocks, are the two alternative methods to this matrix completion. And what we have on the x-axis corresponds to the number of units. Remember, we're holding the overall block size constant, but some of them we have more units missing, and some of them we have more time periods missing. And so what this matrix completion approach with the factors is, it's something in between regressing one column on the other columns or regressing one row on the other rows. It's kind of finding the overall structure of what's happening in the data. And so that method works well, and you can use it whether or not you have, lots of states and not very many time periods, or lots of time periods and not very many states. Or in this case, this is time periods and stocks. So this matrix completion method kind of works well across the board. And it has some specific advantages kind of in the middle. So Then another type of application, and this now comes back to the question that was asked in the break about, can we also use matrix factorization with structural models? So here I have a project with Rob Donnelly and also with some co-authors from Columbia, David Bly is a computer scientist, and Fran Ruiz. And there we're going to combine matrix factorization with the kinds of models we use in IO and marketing to understand the impact of price changes. So here we have scanner data from supermarkets, and the kinds of economic questions we might ask are, how do I optimize prices, and can I personalize prices? So in this case, we're going to be using Logit models. That's what we use in economics and marketing for this. And in the Logit models, you start by modeling somebody's mean utility for a product, and then their overall utility is their mean utility plus an idiosyncratic error term that's usually type 1 extreme value, the Logit error, we call it. And the reason we use that functional form is that if you use that functional form, then the probability that user U buys item I at time t can be expressed with this functional form. It's e to the mean utility divided by the sum of e to the mean utilities of all of the items. So that's just a little algebraic fact, figured out a long time ago. And so the reason this is useful is because we can connect a Logit estimation approach to a structural utility model. So if I can estimate the parameters of your mean utility, you can interpret those as the parameters of your utility function, and then we can do counterfactuals. And so in IO, we use this to do something like say, well, what happens if two firms merge? Or what happens if a new product, if a product exits or something like that? This model will tell you if you take a product away, how those users will get redistributed to other items. And it tells you that in the specific utility maximization framework. Now, so where does matrix factorization come in? Well, typically we put a lot of restrictions on the functional form. So in principle, each user U might have their own separate utility for each item I. But in practice, we may not have enough data about each user U buying each item I to really figure out what each user's utility for that is. And so in this case, matrix factorization would be used to try to reduce the dimensionality of the product space. So I would say, there's actually some fundamental characteristics of products, like maybe they're organic or maybe they're, store brand or other stuff. There's a smaller number of dimensions of the product, and each user is going to have preferences for that lower dimension, and each product has a set of attributes. So I'm going to, instead of having to estimate a separate fixed effect for each user in each item, instead, I'm just going to characterize each user by their preferences for those lower dimensional items. And so then the matrix factorization is going to allow me to express that in this lower dimension. So instead, if there was 1,000 products, instead of each user having 1,000 different product preferences, instead maybe each user is characterized by a 10-dimensional utility function. And we're going to use matrix factorization to figure out what that is. So the way that we do this is we can write the mean utility as the dot product of a vector. Beta U is a vector of the user's preferences, and theta I is a vector of item characteristics. And so each user's mean utility has this user item specific latent, but it can characterize by the dot product of this low dimensions. And then we also can add in nesting for the outside good, because most people don't buy things most of the time. So there's this additional stage of modeling. Just, are you even interested in this product category or not? So there's more details. We estimate it using machine learning. It turns out historically we use Bayesian models in economics, but they have a terrible time scaling. And instead we use two things, one called variational Bayes and another called stochastic gradient descent. These are two computational techniques that allow us to estimate this model. Instead of taking a month on the supercomputer, you can estimate it in an hour or two. And if you're interested, stochastic gradient descent is something you should read about. It's a really, really important innovation in any type of of computational work in any kind of more complicated estimation. So what we do then is we compare different models, and we, in particular, what we would have done historically in economics is we would study, toilet paper separately from apples, separately from cereal. And instead, we put together all the products in the supermarket. We allow that people buy the products, think separately about apples, and apples don't compete with paper towels. But we learn that you might like organic products by the fact that you buy organic apples. And you might also like, some eco-brand paper towels. And so we would learn there's some latent characteristic that in order to model your preferences, and we look and see how much better you do. So again, here's a picture that compares models. In this case, I'm using log likelihood. So my model is red, and it's the best is at the top of the chart, showing that my model beats these other models. And basically the idea is that it's showing that this matrix factorization approach allows us to share information across multiple products. And again, the alternative is category by category estimation, which actually allows there to be more parameters potentially estimated, but you don't have enough data to really do it well. So we're showing that sharing information across products is effective. And then the last picture I'll show is, I know we're getting close to the end here, but I talked in the introduction about how difficult and challenging it can be to show that your model works. So I built, the traditional economic approach was, the god of econometrics told me that here's the functional form, and then the theory tells me that if I have lots of data, I can estimate the parameters well. My machine learning approach was, no, I don't think there's really 20 factors in the world for the supermarket problem, but machine learning told me that 20 factors was a good approximation. That was the one that fit the data, so that's what I used. And there's details in the paper. We optimize a bit for counterfactuals, but to a first approximation, it's goodness of fit. So how do I show you then, if I've thrown out the theory, how do I prove to you that my model has actually done a good job estimating price coefficients, where price coefficients might be what's important for my counterfactual? So here's one example. What we did was we held out data in a test set. And in particular, we held out specific instances of pairs of days around price changes. So all the prices in my data change on Tuesday night. That's actually kind of a supermarket thing. So we took data from Tuesdays and Wednesdays where the price changed for a certain product. And then we held out a certain number of trips around those price changes. Then we categorized the people into how big the response we predicted they would be with the model. So again, we've got held out test data, but we've got other data from these people. So we can say from that other data that wasn't held out for these people, do we think they're price sensitive or not? And then we check whether the comparison from the Wednesday people with, say, a high price to the Tuesday people with a low price is whether that change in each cell is bigger for the cells of people that we said should respond for the price change versus the people who didn't. So we have three groups of people, and we can compare. We can't really get the counterfactual for each person, but we have some people who came on Wednesday and some who came on Tuesday. And we take the subset of those that we think are very price sensitive. And so these dark red are the people that we think are price sensitive. And it turns out on Tuesday to Wednesday changes where there was a big decrease in price, that group, the red group, looks like they had really big responses. And the same thing when, when the prices increase was really big, the red group had the biggest response. That was what our machine learning model said should have the biggest response. So this picture, it's on held out data, and it's a way of showing that my model did a good job correctly classifying who is a price sensitive person and who is not a price sensitive person by putting them into three groups and then comparing the responsiveness of the price changes within those three groups. So this is like, this isn't like a formula somebody gave me. This is like, I understand what problem I'm trying to solve. And then I'm going to create an exercise that is going to be designed to illustrate whether my model is trustworthy for the counterfactuals of interest. And, of course, there's some commonalities to how you do this. It's not completely separate every time, But there is a little bit of like it's being bespoke, that you have a specific setting, a specific data generating process, a specific counterfactual. And so how exactly you prove to your audience that your model is good for doing counterfactuals, maybe tailored to that setting and that circumstance.